Hey all, it's Mooch. Welcome to Minding a Mechs. Today we are testing the heavy hitter collaboration between Timesvape, Heavy Metal Vapor, and TenaciousTX Vapes, Stan. This is the copper, all copper one, gold-plated contacts over a copper base, and then the rest is copper. It ships with straight-sided 28 millimeter top cap, I believe it's 28, and then an angled one, 26. This is what was on the device when I got it, so that's what I'm testing it with. There's not going to be any difference in the voltage drop between these two, so I'm not too worried. I have the usual setup, an electronic load drawing a fixed 30 amps no matter what happens from a 60 amp power supply sitting above it, and we can read, it's set power supply set 3.5 volts, we can read that now. This meter is reading the voltage across the post of the atomizer, and by using a solid aluminum slug inside the device, we allow the current to pass through it, and we can read the voltage drop across the two posts, which is the total voltage drop of the atomizer, the aluminum slug, and the mech. I then subtract the effect of the atomizer and the slug from the numbers that we get here, and in the table that I post, link in the description section below, we calculate the power lost at 30 amps, about 105 watt vape equivalent, and you can directly compare the performance of just the mech itself. And let's get started. And I love this bayonet mount. Just that. Love that. And what we'll do is we'll check here. When I press the button, we get 0 volts, which is good because there's no current flowing through it, so there's no voltage drop. And what I'm going to do now, so I can have consistent button presses, I want to put some friction tape on this beautiful device just for the testing, just to make it easier for me and to make more consistent testing. It is not pretty, but it is functional. Okay, that'll give me a nice grip. Going to 0. Now, to prevent arcing marks from affecting the performance or affecting the testing, particularly if I want to come back and retest, what I do is I press the button to close the contacts. No current will flow. You'll see this will stay at 0 amps. What I then do is press this button to get a 2-second pulse of current at 30 amps. We'll be able to read the voltage here. Then when the pulse stops, I let go of the contact, so there's never any arcing. We'll do separate arcing testing later in the video, and we'll take a close look at the contacts to see how much arcing damage there is, because every contact will have a little bit of arcing damage, and compare that to other devices that I've tested. And we'll go to 0 and fire a pulse. You'll read the voltage off here, about 0.077, 0.09, 0.09. I've gotten some 0.12. I've gotten lower numbers and higher numbers in other tests I've done. I'm going to take that off, take that out. I'm going to try again. And there, now a smaller number, 0.05, which is fantastic. But I believe, let's see if it's, I just loosen this up just slightly. Is that the cause of the inconsistency there? No, actually, that's a terrific number. If I go all the way on, now it's reading fantastic. And I'm going to go by these numbers here. I'd say just make sure I did this extra tight. Just make sure, hopefully you can still get it undone, but screw on the top cap tightly and then screw it tightly to the atomizer, because these are electrical connections you're making. And let's fire this up. 45 millivolts, 0.045, which is fantastic. 45. 52. I'm varying my button where I'm putting my finger a little bit. 71. This is towards the edge. 110. Okay. Another edge. 0.16, 0.18. A different edge. 47. A fourth edge. 60. Back to the center. 64. This is hard to pick a number for. We take this off. I'll rotate it a little bit. Actually, looks like it just goes in the one way. Put it on securely. Now it's like 72, 88, 90 if I go to a different point. 88, 90 if I go to a different point. Let's take it off. Put it back on hard. Make sure it's unlocked. And back to 42, 43. Okay, so what it looks like is it's very sensitive to how you put it on, the bayonet mount. I would recommend, quickly, boom, as hard as you can into position. Though it seemed, if I backed off, and I did, I'm still getting a good number. But then if I take it off and put it back on again, I'm just going to slowly put it on. Ha! And I get a great number, 0.045. I don't know how to. Okay, I'm going to an edge, 37, which is even better. 43, 34. I might be taking down some high points too. That's something I haven't considered here. Okay, I'm going to turn this on and take it off a few times. You won't have to watch me. Okay, let's see what happens after about a dozen times of taking it off and letting it scrape and putting it back into place again. Oh, about the same. 40, 45, 40 something. I'm going to call it 45, with a possibility of going up to like 80 or 90. And I want to be able to say what causes that issue with going up to 0.09, 0.12. Okay, there's me just kind of putting it on gently. There it is. Okay, so that was 0.084. And this is just me just kind of slowly putting it on. 0.045. And here it is. Okay, there it is, solidly into place. 0.035, a fantastic number. I'm going to stick with 0.045. That's very good. I think it was 0.032 was the best I've ever seen. So that's a good number. I'll throw the wattage up on the screen, and you'll certainly be able to see in the table what it is. When I had first gotten this mech and I was doing some tests, I was getting anywhere from 0.06 to 0.12. That's about 1.1 to 3.1 watts. Not good numbers at all. Now, the performance has gotten much better after using it a bunch, and also it's gotten a lot more consistent. Now, that depends, as you saw, it depends a lot on how this is being put on, the bayonet mount. So I think something's being broken in, either a burr or high points or something being rubbed down or something like that, where it can be more consistent, but also better in performance overall. So hopefully it just improves. And what I think a lot we'll be able to see is with the arcing tests, when we do that, which is we're going to fire up right now, be able to see how this thing does and where the arcing occurs. Using a rewrapped Samsung 30T and a 0.1 ohm load. And what I'm going to do is I'm going to fire the mech 200 times. You won't have to watch that. And then we're going to take a look at the contacts and see how much arcing damage there was. And firing away. 1, 2, 3, 196, 197, 198, 199, 200. Okay, not too bad. It's a nice, easier button press. And let's take a look. And here's the constant contact here. Of course, that's up against the battery the entire time. The gold-plated pin ball contact there, and then the cup. And the ball gets, when you press, oops, the button, the ball is forced up into the cup to make contact and up to the battery here. And so we're looking for our arcing marks on the inside of the cup here, but we also want to look once you pass from the cup to the ball, then from the ball it has to come out the sides to touch. It'll get here, and this will carry the current into the body of the device. So while this is sitting in here, the current enters in the top of the ball and then passes out the sides and go into the device. So we've got to look at around here, up on top, and at the cup. And I'm going to start at the top and use a loop, look at the cup, and I'll throw up a macro photograph that you'll be able to see also. And looking down inside the cup, and I see a lot of machining marks, but I don't see arcing marks. Well, just barely, maybe. Let's look at the contact here. Okay, so I see lots of tiny arcing marks all around the base of the pin. So nothing, it's not contacting here, it's all contacting down here near the base. And I think that's what I saw also with the keen. But that's not bad at all. It it doesn't look like it's blasted after 200 presses. Doesn't look like it's blasted through the plating yet. Eventually it will. That's one thing I don't like about gold plating, because the arcing, great for maintenance, fantastic for maintenance. Doesn't affect conductivity to any point because there's so much more base metal. But the arcing can blast it away. And now I'm going to check for any arcing on the inside of this, and this is a little harder to check, and I'm seeing very little, if anything. It's fantastic to see. Checking other contact points, I thought that maybe this block would also end up conducting current as it engaged down inside here, so I just want to check this block. But with so little arcing on what are I consider the main contact points, I can't tell if I'm seeing wear, tiny bits of wear, or tiny arcing marks. So there's very little arcing, and that's wonderful to see because that makes maintenance easier. The gold plating isn't blasting off in 20 presses or something like that. So I love seeing that. The amount of machining marks and stuff in here, maybe that's affecting conductivity a little bit, but that 0.045 is pretty good. It's just making sure you get this, put up into the device solidly to get the lowest voltage drop possible. So overall, with a 0.45 volt drop, fantastic performer. I love the bayonet mount. Very little arcing damage. I'm really impressed. This is a nice device. I took a break from testing because I wanted to give some thought as to what was going on with the performance here and go over very carefully this with a 10 power magnifier and try to find out what was causing the inconsistencies here and why I got better performance when I took the button on and off a few times. And I think I have the solution, or I think I found out what was going on. Now, underneath the lugs here, this is where it engages the slots in here. Comes down and rotates in the slot in the 3 sets of lug and slot. And I noticed underneath the lug here, it was quite rough, scratched, and there were little particles of copper here. So I think there were some rough spots in the machining in the slots. And by going back and forth, I was taking off those high spots, giving a greater size contact patch. I also noticed a little bit of a burr on the machining of the slot, and I can also push it out of the way or reduce the contact patch, the size of the contact that the lug and the metal is actually making. And by going back and forth a few times, I started smoothing it out. I started making it easier for it to make contact, and the performance improved. I tried doing it maybe 30, 40 more times. Be very careful not to damage your O-ring. You may want to take the O-ring off carefully, and then do this, and you would pull on the button while you're doing it to simulate what the O-ring does, and just go back and forth. And now the action's a lot smoother, it's more consistent in its power loss, and the final numbers, the 0.05 volt drop, when you do all the calculations to subtract the effect of the atomizer, etc., is about 0.8 watts lost for a 105 watt vape, which is pretty good performance. If you don't get the button just right, if you get it in all the way and it's making great contact, but if it's backed off too far or you haven't taken care of the burrs or something like that, the power loss, it's just really smooth now. I like that. Then the power loss can go as high as 2.2 watts. That's not so great. So I recommend breaking it in and keeping this clean. Now, there is arcing forming down inside here. It's very tiny, it's very minor, but in the slots, eventually you're going to have to get in there with a Scotch-Brite pad or something and take down the high spots. Well, the high spots you can probably take down just by going back and forth, but you want to keep it clean in there because that's a contact point, these 3 slots in here, and the underside of each of the 3 lugs. This is part of your maintenance in addition to keeping the battery contact clean and also keeping the ball and cup, getting the arcing spots off there eventually, but it doesn't arc much. Nowhere does it arc much. This is just little things to do eventually over time that you have to take care of. So the things I like about this mech, because I do like it, is the venting slots are absolutely huge up here, which I really like. Not just little tiny holes, but actual look like good functioning thermal runaway, get the gas out of this mech so it doesn't blow up venting slots. I love the bayonet mount. Once it's broken in, it is smooth. For safety, it's great to get it out quick. It's fully lined, downward lining, which I like. There's a insulator up at the top, so you don't have to worry about a damaged wrapped cell going up there, and you press the button without a atomizer attached. A damaged cell could cause a short circuit. It's got a terrific lock. Okay, unlocked there, locked there. It doesn't, I tried it in my pocket for a little bit. It's not going to actuate accidentally. It's got a nice long throw on it, spin on it, and it's good performance. 0.8 watt loss is fantastic. Yes, there are a couple of mods that perform about a half watt better, but that's at 105 watts. So this thing's doing just fine on its own with that loss, and you get all the other benefits of the constant contact switch, the bayonet mount, the huge slots and all. So the heavy hitter is a mech that I like, and I'm glad I had the chance to test it. Even though there wasn't much power loss in this mech, I was curious to whether the voltage drop, the power loss, was occurring at the lugs. Here, I think there's 3 lugs for the bayonet mount for the button housing, or whether they're occurring deep inside where the contacts are, or both. So I'm going to do some thermal imaging to take a peek. I'm going to pass a continuous 30 amps through the device, not because that simulates how it's going to be used, but that's how we force the device to start to heat up. And wherever heat is occurring, that's where there's resistance, and where there's resistance, that's where we're losing the power. That's where the voltage drop is occurring. I have the device wrapped in black electrical tape because polished copper is a lousy emitter of infrared radiation, and you can't see what the actual temperature is. You can see some spots where I don't have the tape. You see the reflection of my hot hand, but if I remove my hand, you just see cool blue copper, and you won't be able to see the temperature of the copper where there's no tape. You're just going to see the temperature of the reflections in the copper. At the bottom I have a rubber button or rubber bumper attached to the button of the mech, and that's to keep my finger heat from heating up the button. But we will be able to look down here, and if the copper button looks hot, that means it's conducting heat out from the inside where the contacts are. And let's start passing 30 amps continuous through this mech. And because the power loss is pretty small, I don't expect this to heat up very quickly at all. Though we see some little bit heating in the button. Again, remember, my hands are white hot, quote unquote, so that's body temperature. So the mech now is still not even up to body temperature, but we can see the button now, and you can see the dividing line between the button and the housing. Button's heating up a couple degrees or so. And what we can do is we can rotate it around, looking for those hot spots. I'm going to let go. And I see pretty even heating here, where if there's the lugs were the cause of any kind of power loss, we would see increased temperatures there. And I'm passing 30 amps through it again. Okay, let's take a look at the button. Okay, you can see the button here is red about my body temperature, and it's not from me pressing it, because remember there's this thick rubber bumper on there. That's heat being conducted out from the contacts. But I'm not seeing any hot spots as I rotate this around. So for me, that tells me that the heat is coming from the cup and ball contact, or the contact, the gold-plated copper contact pin is touching the copper housing. So no hot spots from the bayonet mount. That's looking good. And that's the thermal imaging of the heavy hitter Mech mod. That's all for today. Thank you for watching.